Availability is a security property. Opening, the question nobody asks until it's too late. Here is a strange exercise. Walk into any organization and ask the security team to describe their worst day. Most of them will describe a breach, stolen credentials, an attacker moving laterally, data leaving through a channel nobody was watching. Almost nobody describes their worst day as the website was down for 6 hours and nobody could log in. And yet for the business, for the customer trying to check their account balance, for the hospital trying to pull up a patient's chart, for the trading desk trying to execute an order before the market moves, those 6 hours of downtime are not an IT problem. They are a security failure, every bit as real as a data exfiltration event. The data was never stolen. Nothing was tampered with, and the system still failed at the thing it existed to do. This is the idea sitting underneath everything we are going to talk about today. Security is not just about keeping people out. It is about keeping the system running for the people who are supposed to be in. A system that is perfectly locked down, perfectly encrypted, and perfectly offline has achieved confidentiality and integrity at the cost of the third leg of the stool, and in doing so, it has failed completely. A vault that nobody can open, including the bank, is not a secure vault. It is a very expensive paperweight. So let's spend our time today on the leg of the triad that gets the least attention in casual conversation. But that shows up first when something goes wrong, and that the business actually feels in its bones the moment it's gone. Availability. The foundation, what the triad actually promises. Confidentiality, integrity, availability. Most people memorize this as a 3-word incantation early in their security education and never revisit it again. But each of these words is a promise, and the promises can conflict. Confidentiality is the promise that information is seen only by those who are supposed to see it. You deliver on this promise through encryption, through access control lists, through the principle of least privilege, giving people only the access they need and nothing more. Integrity is the promise that information is accurate and unaltered. You deliver on this through checksums, through digital signatures, through version control and immutable logging. If you pull a record today, it should be exactly what was written, with nothing quietly changed in between. Availability is the promise that the system responds when a legitimate user needs it to. You deliver on this through redundancy, having more than one of everything that matters, through load balancing, through disaster recovery planning, through backups that you have actually tested, not just configured and forgotten. Here is the part that gets glossed over. Availability is not the easy or obvious one. It is arguably the hardest to reason about because it is the property that is most directly in tension with the other two. Every confidentiality control adds a checkpoint. Every integrity control adds a verification step. Checkpoints and verification steps take time, and time is exactly what availability is trying to minimize. The emergency room doctor who needs a patient's medication history right now does not have time for a 30-second multi-factor prompt. The trading firm whose competitive edge lives in microseconds cannot afford a firewall that inspects every packet at the application layer. In both cases, the more secure option, evaluated purely on confidentiality or integrity grounds, is the less secure option overall, because it sacrifices availability to a degree the business cannot survive. This is why availability as a security property is not a throwaway line tacked onto the end of the triad. It is the property that keeps the other two honest. A confidentiality control that destroys availability has not made the system more secure. It has made the system useless, and a useless system gets worked around, which usually means it gets bypassed in ways that destroy confidentiality anyway. Now let's get specific about what threatens availability, because The system needs to stay up is too vague to design around. A denial of service attack, in its simplest form, is an attempt to make a resource unavailable to its intended users, not by breaking in, not by stealing anything, but simply by overwhelming it. Think of it as the digital equivalent of 1,000 people calling a restaurant at the exact same second, asking to make a reservation, until the phone lines are so jammed that the one customer who actually wants to order dinner can't get through. A distributed denial of service attack is the same idea, scaled out across potentially hundreds of thousands of compromised devices. A botnet, each sending a small amount of traffic, but in aggregate producing a flood that no single server and often no single data center can absorb. The reason DoS and DDoS sit squarely inside the security conversation, rather than being filed under network performance, is that they are deliberate, often financially or politically motivated, and they are frequently a smokescreen. A sustained DDoS attack against the public-facing website can be a distraction technique, while a separate, quieter intrusion targets the internal network, betting that the security team's attention is consumed fighting the visible fire. Then there's the planning side of availability, which is where business continuity planning and disaster recovery planning come in, and these two terms get conflated constantly, so let's separate them properly. A business continuity plan is the broader document. It answers the question, if something disruptive happens, a fire, a flood, a pandemic, a ransomware attack, a key supplier going bankrupt, how does the business keep operating? It covers people, processes, alternate work locations, communication plans, and yes, technology. A disaster recovery plan is the technology-focused subset of that. It answers the narrower question, how do we get our systems, applications, and data back online and how quickly? The BCP might say, if our primary data center is destroyed, customer service staff will relocate to the backup office and use the failover call center system within 4 hours. The DRP is the technical playbook underneath that promise, the actual steps to bring up the failover database, redirect DNS, and verify data integrity before declaring the systems live again. You cannot have a credible BCP without a tested DRP underneath it, and a DRP that has never been tested is, in practice, a piece of fiction with a professional-looking cover page. The tension, the control that protects you is the control that can take you down. Here is the central tension that we are going to keep returning to throughout this session, and it is worth stating plainly because it is counterintuitive the first time you hear it. The very mechanisms designed to protect a system's confidentiality and integrity are among the most common causes of availability failures. An intrusion prevention system is designed to protect the network by automatically blocking traffic that matches a malicious signature. That is its job, and when it works, it is invaluable. It stops an attack inline in real time without waiting for a human to react. But an IPS that updates its signature database and then starts matching a pattern in legitimate application traffic, perhaps a financial application that sends data in a format that superficially resembles a known exploit, will block that legitimate traffic with exactly the same confidence and the same lack of hesitation that it would block a real attack. From the perspective of the business, the security control has become indistinguishable from an attacker. It has taken down the very system it was protecting. A null root, the blunt instrument used during a DDoS attack, is the same idea taken to its extreme. When a flood of traffic threatens to overwhelm a database or exhaust a network's capacity, the fastest way to stop the flood is to tell the upstream provider to drop all traffic destined for that IP address, all of it good and bad alike. The attack stops instantly. So does the business. You have achieved a strange kind of victory. The attacker's traffic is no longer reaching you, but neither is anyone else's, which means the attacker has, in effect, succeeded at their actual goal, which was never to get in. It was to make you unavailable, and a null root accomplishes that for them, just using your own infrastructure to do it. This is the tension. Confidentiality and integrity controls are, by their nature, things that say no. Availability is the property that depends on the system saying yes to the people who are supposed to get a yes. Every no mechanism you add is a potential false no to a legitimate user, and the more aggressive and automated that no mechanism is, the larger and faster that potential failure can be. Understanding availability as a security property means understanding that your defenses have to be designed with their own failure modes in mind. Because a defense that fails by going silent is very different from a defense that fails by blocking everything. Architectural philosophy, designing for the system that will eventually break. If confidentiality-focused architecture is about building walls, and integrity-focused architecture is about building tamper evidence into everything, then availability-focused architecture starts from a much blunter premise. Something, somewhere, will fail, and the design has to survive that failure without anyone outside the organization noticing. This is the philosophy of resilience, and it shows up as redundancy at every layer. Not redundancy as in, we bought 2 of everything and hope one never breaks, but redundancy as in, we have built the system so that the failure of any single component is a non-event. A server fails, and traffic is already flowing to its siblings before a human is even paged. A data center loses power, and the application is already serving from a second region. A database corrupts, and a verified, immutable backup from 12 hours ago is ready to be restored in minutes, not days. The architectural shift this requires is significant. Traditional security architecture often treats the system as a single thing that needs to be defended. Availability-focused architecture treats the system as a population of interchangeable, disposable components, any of which can be lost without losing the system itself. This is the thinking behind auto-scaling groups that can replace an unhealthy server automatically, behind multi-region cloud deployments, and behind the entire discipline of chaos engineering, where organizations deliberately break parts of their own production systems to prove that the redundancy actually works, rather than assuming it does because a diagram says so. It also means that availability architecture has to think about the attacker's economics, not just the defender's. A DDoS attack is, fundamentally, a cost asymmetry attack. The attacker spends very little to generate traffic, and historically, the defender had to spend an enormous amount to absorb it. Modern availability architecture flips that asymmetry back. Cloud-based scrubbing services operate at a scale that dwarfs almost any individual attack, absorbing hundreds of gigabits of traffic as a matter of routine, which means the attacker's cost per impact drops towards 0 from their perspective. But the defender's cost per impact also drops, because the defense is shared infrastructure rather than dedicated capacity sitting mostly idle. The through line here is that availability is never solved by a single control. It is solved by a system that assumes its own components will fail, that has already rehearsed what happens when they do, and that has made the cost of attacking it economically unattractive rather than merely technically difficult. The tools and what they actually cost you. Let's walk through the tools that show up again and again in availability conversations, and let's be honest about each one, not just what it provides, but what it costs to run and what it quietly does not cover. Load balancers are the most foundational tool in this list. A load balancer sits in front of a pool of servers and distributes incoming requests across them, so that no single server becomes a bottleneck, and so that the failure of one server doesn't take the whole service down with it. The benefit is obvious. You get both performance and resilience from the same piece of infrastructure. What it costs you is complexity in session management. If a user's shopping cart or login session is tied to the specific server they first connected to, and the load balancer sends their next request to a different server, that session can simply vanish unless you've built shared session storage or sticky sessions into the design. And what it does not cover is a failure of the load balancer itself, which is why production environments run load balancers in pairs or clusters, because the single most dangerous single point of failure in a redundant architecture is the redundancy mechanism itself. DDoS mitigation services, the cloud-based scrubbing providers, work by sitting between the internet and your infrastructure, absorbing and filtering traffic before it ever reaches you. The benefit is scale that almost no individual organization could build for itself. These providers handle traffic volumes in the terabits per second across their global network. What it costs you is, first, money. On-demand scrubbing during an active attack can carry a steep premium compared to always-on protection. And second, latency. Every legitimate request now has to travel through the scrubbing provider's infrastructure before reaching you, adding tens of milliseconds that, for most applications, are invisible, but for latency-sensitive applications, are not. What it does not cover is application layer logic flaws. A scrubbing service is extremely good at recognizing this traffic pattern looks like a flood. It is much less effective against a smaller-scale attack that exploits an expensive database query, sending a modest number of requests that each take 10 seconds to process on your end. Traffic volume looks normal to the scrubber, but your servers are still being ground to a halt. Immutable backups are the availability tool that exists specifically for the worst-case scenario: ransomware. A normal backup can be encrypted right alongside your production data if the ransomware has write access to wherever the backup lives. An immutable backup is written once and then made structurally impossible to modify or delete for a defined retention period, even by an administrator account, even by the backup software itself. The benefit is that ransomware recovery becomes a restoration exercise rather than a negotiation with criminals. What it costs you is storage. Keeping multiple immutable snapshots over time multiplies your storage footprint. And immutability, by definition, means you can't simply delete old data to save space until the retention lock expires. What it does not cover is the time to restore. An immutable backup that takes 18 hours to restore a multi-terabyte database is available in the sense that the data exists and is trustworthy. But the business is still down for 18 hours, which is why backup strategy and recovery time objectives have to be designed together, not separately. Auto-scaling is the tool that protects against a failure mode that often gets overlooked in security conversations. Success. A marketing campaign goes viral, a product launch gets unexpected press coverage, and suddenly legitimate demand spikes far beyond what the normal infrastructure footprint can handle. Auto-scaling watches load metrics and automatically provisions additional capacity, more servers, more containers to absorb the spike, then scales back down once it passes. The benefit is that you stop treating too many real customers as an outage waiting to happen. What it costs you is, again, money, but in a less predictable way than fixed infrastructure, a poorly configured auto-scaling policy, or worse, a DDoS attack that the scrubbing layer hasn't caught, can trigger runaway scaling that generates a massive, unexpected cloud bill, sometimes called an economic denial of sustainability attack, where the goal isn't to take you offline, but to make staying online prohibitively expensive. And what it does not cover is anything downstream of the compute layer that doesn't scale as elastically. A database with a fixed connection limit, or a third-party API with a rate limit, can become the new bottleneck the moment you've successfully auto-scaled everything in front of it. Each of these tools, examined honestly, tells the same story. They each solve a real failure mode. They each introduce a new cost, a new complexity, or a new failure mode of their own. None of them is the answer. All of them together, with the gaps between them understood and covered, start to look like resilience. Implementation, where the thresholds actually get decided. Let's take two implementation scenarios and work through the decisions that actually have to get made. Because implement a load balancer and implement a BCP sound like checkbox items until you sit down and have to pick the numbers. Start with the load balancer. The technical deployment, provisioning the load balancer, registering the backend servers, configuring health checks, is the easy part, and most engineers can do it in an afternoon. The decisions that take longer and that determine whether the deployment actually improves availability or just adds a new component that can fail are about the health check configuration and the failover behavior. How often does the load balancer check whether a backend server is healthy? Check too infrequently, and a failed server keeps receiving traffic for minutes before it's pulled out of rotation, during which every user routed to it experiences errors. Check too aggressively, and a server that's simply under heavy but legitimate load, perhaps it's running a scheduled batch job, gets marked unhealthy and removed, reducing your effective capacity at exactly the moment you need it most, which can cascade. Removing one server increases load on the remaining ones, which might then also fail their health checks, and you've turned a minor blip into a self-inflicted outage. Then there's the question of what the health check actually checks. A health check that only verifies, is the web server process responding on port 443, will report a server as healthy even if that web server can no longer reach the database behind it. Meaning, the load balancer happily sends users to a server that will return errors for every request. A more meaningful health check exercises a lightweight but representative path through the application, confirming that the dependencies the application actually needs are reachable. The trade-off is that a deeper health check takes longer to run and consumes more resources on the backend. So you're balancing the fidelity of your health signal against the overhead of generating it. Now the business continuity plan. The temptation when asked to implement a BCP is to start writing a document, and that's exactly backwards. The first step is not writing, it's a business impact analysis. You need to know for every critical business process what the actual cost of an outage is expressed in time. If the order processing system is down for 15 minutes, that's an inconvenience. If it's down for 4 hours, you've missed a settlement deadline with financial penalties. If it's down for 24 hours, customers start canceling contracts. These thresholds become your recovery time objectives, the maximum acceptable time to restore a function, and your recovery point objectives, the maximum acceptable amount of data loss, measured in time, which determines how frequently you need to be backing up or replicating that data. Only once those numbers exist for every critical process can you design the technical recovery plan underneath them, because the numbers determine the architecture. A recovery time objective of 15 minutes for a database means you need a warm or hot standby that's already running and synchronized. You cannot restore a backup from tape in 15 minutes, no matter how good your tape is. A recovery time objective of 24 hours for an internal reporting system might mean a cold backup that's restored on demand is perfectly adequate, and spending money on a hot standby for that system would be solving a problem the business doesn't actually have. The part of BCP implementation that gets skipped most often, and the part that turns a plan from theater into a real capability, is the test. A BCP that has been written, approved, and filed away, but never exercised, will fail in ways that are entirely predictable in hindsight. The emergency contact list has 3 people who left the company. The documented failover procedure references a server that was decommissioned 18 months ago. And the backup communication channel turns out to be a conference bridge whose phone number nobody actually wrote down anywhere except in the primary system that is, by definition, the thing that's down. A tabletop exercise, walking through a simulated disaster scenario, as a structured discussion rather than a live drill, surfaces these gaps cheaply. A full failover test, where you actually cut traffic over to the disaster recovery site for a defined window, surfaces gaps that tabletop exercises can't, because it's the only way to discover that the identical standby database has configuration drift that's been quietly accumulating for 2 years. And running underneath both of these, the load balancer rollout and the BCP, is the emergency change management question. What happens when a critical patch needs to go out immediately, outside the normal change window, because a vulnerability is being actively exploited? The standard change process exists precisely to protect availability, peer review, staged rollout, a rollback plan, and an emergency process that simply bypasses all of that in the name of speed can turn a security fix into an availability incident of its own. The resolution is not to have no process for emergencies. It's to have a pre-approved, abbreviated process. A smaller approval group empowered to authorize same-day changes. A requirement that the change still be tested in a staging environment even if that testing window is compressed to an hour instead of a week. And a rollback plan that is mandatory, not optional, precisely because emergency changes are the ones most likely to need rolling back. Troubleshooting, when availability breaks and how you find out why. Let's work through 3 failure scenarios properly, not as, here's what was wrong, here's the fix, but as the actual diagnostic walk. The first scenario, an intrusion prevention system recently updated with a new signature set starts dropping legitimate traffic to a critical application. Users report the application is broken, pages time out, transactions fail partway through. The first thing you check is not the application. It's whether anything changed recently in the security stack, because the application was fine yesterday and broken today is a strong signal that something in the path between the user and the application changed, not the application itself. A quick check of the IPS's signature update log shows a new rule set was deployed automatically overnight. That's your first strong lead. The next step is to look at the IPS's own logs for drop or block events correlating with the affected application's traffic, around the time users started reporting problems. If you find a spike in blocked packets to that application's IP and port, starting right after the signature update, you've essentially confirmed the hypothesis, but you still need to know which specific signature is firing because the fix has to be surgical. You pull the specific rule ID being triggered and look at what it's designed to detect. Perhaps it's a rule looking for a pattern associated with a known web shell, and the legitimate application happens to send a parameter in its normal traffic that incidentally matches that pattern. The immediate fix to restore service is to put that specific rule into a monitoring-only mode for that specific application's traffic, not to disable the entire IPS, and not to disable that rule globally, because the rule might be correctly catching real attacks against other systems. The longer-term fix has 2 parts. You report the false positive back to the signature vendor, because if your application triggers it, others probably do too, and you document the exception with an expiration or review date, because temporary exceptions that are never revisited are how security debt accumulates silently. The deeper lesson this scenario teaches is that automated protective updates need a staging or canary deployment, the same as any other change. A signature update is code, deployed to a system that has the authority to block production traffic, and it should be treated with the same caution as any other production deployment with that level of blast radius. The second scenario, ransomware has encrypted the organization's file shares, and the team turns to backups to restore, only to discover the backups are also encrypted. This is the nightmare scenario, and the diagnostic work here happens on 2 tracks simultaneously. The first track is forensic. When did the encryption actually begin versus when was it discovered? Ransomware often sits dormant for days or weeks after initial compromise, quietly spreading and disabling defenses before the encryption payload triggers. If your backup retention only goes back 3 days and the malware has been present for 2 weeks, every backup you have may already be compromised, either directly encrypted or backing up a system that already had the malware's persistence mechanisms embedded in it, which means restoring from that backup just restores the infection. The second track is about why the backups were reachable at all. If a backup repository can be written to, modified, or deleted by an account that an attacker who has gained domain administrator privileges can also access, which is very often the case, because backup systems frequently run with broad service account permissions for convenience, then the backups were never actually a separate line of defense. They were the same line of defense, just with an extra step. The fix has to address both. In the immediate term, you go further back in your backup history than you'd normally need to, looking for the most recent backup that predates the estimated initial compromise. And you restore to an isolated environment first, scanning thoroughly before reconnecting it to the network, because restoring a compromised snapshot back into production just resets the clock on the same problem. In the longer term, the fix is architectural. Backup systems need to be on a separate authentication domain from production, with immutability enforced so that even a fully compromised domain administrator account cannot delete or encrypt the backup data. And the retention window needs to be long enough to cover realistic dwell times, which for sophisticated ransomware operators can be weeks or months, not days. The third scenario. The company website becomes slow, then intermittently unreachable, and the working theory is a DDoS attack. The diagnostic instinct many people have is to immediately start blocking IP addresses. But that's premature. You need to confirm what kind of problem this actually is before you can respond correctly. Because the fix for a volumetric DDoS attack, an application layer attack, and a simple infrastructure failure are all different, and applying the wrong one can make things worse. The first check is volume. Is there an unusual spike in inbound traffic at the network edge, visible in flow data or the CDN's traffic graphs? If yes, and the traffic is coming from a wide, geographically dispersed set of source IPs with no obvious legitimate pattern. For instance, thousands of requests per second to the home page from IP ranges that don't match your normal customer geography. That points toward a volumetric attack. And the response is to engage DDoS scrubbing if it isn't already active, or to raise its sensitivity if it's running in a passive monitoring mode. If the traffic volume looks roughly normal, but the application is still slow, the next check is server-side resource utilization. CPU, memory, database connection pools, query execution times. A small, targeted application layer attack might send a modest number of requests, each one deliberately crafted to trigger an expensive operation, like a search query against an unindexed field or a report generation endpoint that locks a database table. This won't show up as a traffic spike. It'll show up as resource exhaustion on a small number of backend components, and the fix is rate limiting that specific endpoint and, separately, fixing the underlying performance issue that made it exploitable in the first place. And if neither of those checks shows anything unusual, traffic is normal, resources look fine, you've just ruled out an attack, and you're now looking at an infrastructure failure. A misconfigured DNS change that's sending traffic to the wrong place, a certificate that expired overnight, or a recently deployed change that introduced a performance regression. The point of this scenario isn't the specific fix for any one branch. It's that the site is slow, has at least 3 structurally different causes, and jumping straight to the DDoS response when the real problem is an expired certificate means You've spent your incident response budget solving the wrong problem while the actual cause continues unaddressed. The role-based lens, three very different relationships with uptime. The security architect's relationship with availability is almost entirely about decisions made long before anything goes wrong. When an architect is designing the network segmentation for an operational technology environment, the industrial control systems that run physical processes like manufacturing lines or power distribution, availability isn't an abstract concern. It's the dominant one because in OT, a security failure that causes downtime can mean a halted production line, a safety system that can't communicate, or in the most serious cases, a genuine physical safety hazard. If a firewall upgrade between the IT and OT networks introduces a subtle issue, say, the new firewall is doing deep packet inspection on an industrial protocol it doesn't fully understand, introducing latency that causes intermittent communication drops between a controller and a sensor. The architect's job is to recognize that intermittent communication drops in an OT environment is not a networking inconvenience, it's a potential precursor to a safety incident. And the troubleshooting has to proceed with extreme caution. You don't start unplugging things or pushing configuration changes to a live industrial network the way you might in an IT environment, because the cost of getting the diagnosis wrong is measured in production downtime or worse, not just a support ticket. The architect's moment of truth with availability happens at design time, when the segmentation strategy, the failover paths, and the change control process for that environment are decided, long before any specific incident occurs, but in a way that determines how survivable that incident will be. The SOC analyst's relationship with availability is immediate and operational. When anomalous traffic is detected from an internal host to a known command and control server, beaconing out every 10 minutes, the analyst is sitting at the exact intersection of two competing availability concerns. On one hand, that host is compromised, and every 10-minute beacon is an opportunity for the attacker to receive new instructions, escalate, or begin exfiltrating data. The longer it stays connected, the worse the eventual outcome. On the other hand, that host might be a production server, and an analyst who immediately and unilaterally takes it offline without coordination has just caused an availability incident of their own, potentially during a period when the business can least afford it. The disciplined path is containment that preserves availability where possible, blocking the specific outbound connection to the C2 server at the firewall, rather than powering down the host, stops the bleeding without necessarily taking the service down, buying time to coordinate with the system owners, IT operations, and management about a planned, communicated remediation rather than a surprise outage. The analyst's relationship with availability in this moment is about recognizing that stop the attack and stop the business are not the same instruction, even though the fastest version of the first often looks identical to the second. The security automation engineer's relationship with availability is about building systems that protect uptime without requiring a human to be awake and paying attention at 3 in the morning, but also about not letting that automation itself become the availability risk. Consider the challenge of deploying a new version of an automated pipeline, say, the system that ingests security telemetry and triggers alerts. You cannot simply replace the old version with the new one and hope it behaves identically. If the new version has a subtle bug in how it formats alerts, you might go from fully functional alerting to silently broken alerting with no obvious signal that anything changed, because the pipeline is still running, just producing slightly wrong output. The engineer's answer to this is a parallel run strategy. The new version runs alongside the old version, processing the same inputs for a defined period, with its outputs compared against the old version's outputs rather than being sent live. Only once the outputs match, or any differences are understood and intentional, does traffic cut over to the new version. And even then, the old version stays available, dormant, ready for an immediate rollback if something the parallel run didn't catch surfaces in production. The engineer's relationship with availability is fundamentally about never trusting. It worked in testing as sufficient evidence that a change to a live system that protects availability won't itself become the next availability incident. Case scenario: the bank, the flood, and the 48 hours. A regional bank's online banking platform begins experiencing severe degradation on a Tuesday morning. Within 20 minutes, it becomes clear this is not a routine traffic spike. Incoming traffic to the bank's public-facing infrastructure has climbed to roughly 500 gigabits per second, originating from a botnet spread across tens of thousands of compromised devices worldwide. This is a volumetric DDoS attack, and it is large enough that no on-premises infrastructure the bank owns could possibly absorb it directly. The bank's normal internet connectivity tops out at a small fraction of that volume. The attack alone is enough to saturate every upstream link the bank has, regardless of what's happening on the servers behind them. In the war room, the first instinct from part of the team is the one we discussed earlier: null route the traffic. Tell the upstream provider to drop everything destined for the public IP addresses under attack. This would work in the narrowest sense. Within minutes, the flood would stop arriving, and the internal database and application servers, which were beginning to show signs of strain from the sheer volume of connection attempts, would be protected from being overwhelmed entirely. But this is where the central tension of the entire session becomes concrete and immediate. Null routing protects the database by making the bank's online services completely unavailable to everyone, not just the attacker, but every legitimate customer trying to check a balance, pay a bill, or move money before an end-of-day deadline. For a bank, online banking is completely down during business hours is not a contained incident. It's a headline, a regulatory notification trigger, and a direct hit to customer trust that could outlast the technical incident by months. The team would have secured the database by destroying the thing the database existed to support. The actual response reframes the problem rather than accepting the binary of stay up and risk the database versus protect the database and go fully dark. The bank redirects its public DNS records to point at a cloud-based DDoS scrubbing provider, one of the large global networks built specifically to absorb attacks of this scale as a matter of routine. All traffic destined for the bank's online banking platform now flows through the scrubbing provider first. The provider's infrastructure identifies and filters the malicious traffic, the botnet's flood, while passing through the genuine traffic, the actual 1 gigabit or so per second of real customers logging in, checking balances, and making transactions. From the scrubbing provider's network, only that clean traffic is forwarded on to the bank's own infrastructure, which can handle it without any strain at all. The result is that the database stays safe, it never sees the flood, and customers can still log in. The attack, from the attacker's perspective, has failed at its actual objective. They wanted to take the bank offline, generate panic, perhaps extort the bank under threat of a longer attack, or provide cover for some other activity. Instead, the bank's online banking availability holds at roughly 99.9% throughout the entire 48-hour attack. A number that, expressed honestly, still means a small amount of degradation occurred, almost certainly during the attack's initial ramp-up before the scrubbing redirect was fully in place, but a number that is worlds apart from the alternative. This is not a free outcome, and the bank documents the trade-offs explicitly rather than quietly absorbing them. The scrubbing service, especially engaged on an emergency, on-demand basis rather than as a pre-purchased always-on subscription, carries a steep cost. A cost the bank weighs against the cost of even a few hours of full downtime and decides is clearly worth paying, but a cost that becomes a line item in the post-incident review and a driver for reevaluating whether always-on protection should be the new baseline going forward. The redirect through the scrubbing provider adds measurable latency. Every request now takes an extra 20 to 50 milliseconds round trip. And for online banking, that's imperceptible to a human clicking through screens, so it's accepted without hesitation. The bank also makes a forward-looking decision as part of its trade-off documentation. Rather than waiting for the next attack to trigger an emergency, on-demand engagement again, they configure the scrubbing relationship so that it activates automatically once inbound traffic crosses a defined threshold. Say, 10 gigabits per second, rather than requiring a human decision under pressure during the next event. During normal operation, traffic stays well under that threshold, and customers experience the fast, direct path with no added latency at all. The scrubbing layer is there, ready, but invisible until it's needed. What makes this scenario a genuine demonstration of the mental model, rather than just a happy ending, is the documentation that follows it. The decision not to null root, the cost of the scrubbing engagement, the latency trade-off, and the automated activation threshold are all written up as explicit, signed decisions. Not because anything went wrong, but because the next time pressure is high and someone in a war room reaches for the null root option as the obvious fix, there's a documented record of why that's the wrong instinct, what was done instead, and what it cost. The bank didn't achieve perfect security. They achieved availability under attack, which for an online bank is most of what security actually means to the people on the other end of the connection. Closing, the property that makes the others matter. There's a version of security thinking that treats availability as the thing you worry about last. Get confidentiality and integrity locked down first. And availability is just an operational concern, something for the infrastructure team to handle. That ordering has it backwards, and I'd argue it's responsible for a fair number of the worst outcomes in this field. Availability is not the property you get to after the real security work is done. It's the property that determines whether anyone ever experiences the benefit of the other two. A system with perfect confidentiality that nobody can use isn't protecting anyone's data. It's just storing it somewhere nobody can verify, including the people who are supposed to be able to. A system with perfect integrity that's offline isn't preserving the accuracy of anything that matters to anyone right now. What I want you to carry forward isn't a checklist of redundancy patterns, although those matter. It's a habit of asking, every time you design or evaluate a control, what happens to availability if this control behaves exactly as designed, but at the worst possible moment against the wrong target? The IPS that blocks a real attack is doing its job. The IPS that blocks your own payment processing traffic during a signature update is doing exactly the same thing, matching a pattern and acting on it. And the difference between those two outcomes isn't a flaw in the IPS. It's a gap in how the system around the IPS was designed to fail. Build with the assumption that things will fail, components, controls, assumptions about what normal traffic looks like, and ask not just, how do we prevent this? But when this happens anyway, who notices, how fast, and what do they do? That question, asked consistently, is what separates a security posture that looks good in a diagram from one that survives contact with a Tuesday morning that goes very wrong. End of session, mental model. Availability is a security property,